So acids and bases, man, the first definition that you get for acids and bases comes in like elementary school. And in fact, my son, he's 8 years old. He asked me what I was teaching tonight. And I said, oh, I'm teaching acids and bases tonight. And he said, what is that? I gave him the stereotypical elementary school definition where, oh, acids are sour things and bases are bitter things, right? Like that's the first experience we get with it, or the first definition we get for acids is based on taste. Obviously, it's not that simple anymore. And as a chemist, you're not going to make it very long if you just go around tasting everything to see if it's acidic or basic, right? Eventually, that's going to catch up to you. So we got some better definitions. The first person to put a real definition on it that wasn't qualitative, like your sense of taste. First person to do that was our man Svante Arrhenius, right? That man has got his finger in every branch of chemistry, right? He did a little bit of everything. He was a real Renaissance chemist. So this is like 1800s, and Svante Arrhenius says, well, acids are substances that produce the H plus ion in water. So an acid is something that when you dissolve it in water makes H plus ions. And he says bases are substances that when you dissolve them in water produce hydroxide ions. So this is the first of three definitions of acids and bases that you're going to need to have memorized. So make sure you get this definition. This definition is not great. There are better definitions, but it is the first, so give Svante Arrhenius some credit, right? Each definition attempts to improve upon this definition, although for the 1800s, Svante Arrhenius does a decent job. The first issue with this definition is it only works if the solvent is water. So that's kind of crappy, right? Like, what if my solvent is dichloromethane or ethanol or acetonitrile or benzene or something? Like, what if I have a different solvent? Well, the Arrhenius definition isn't going to work great, so it only works if the solvent's water. And the second problem is with this. The H plus ion, we now know, does not actually exist. In fact, in the biz, we call an H plus ion a naked proton. So let's talk about why we call that a naked proton. Hang on, how do I get out of here? You think this is my first time on Zoom, right? But they keep changing stuff on me. Let's talk about why we call the H plus ion a naked proton and why it doesn't actually exist in solution. If you look at a periodic table, I'm going to take you back to Chem 101. We're going to do nuclear notation. 99.9% of the hydrogen on this planet is hydrogen 1. Okay, so that's 1. Remember, that's the mass number. That's the protons plus the neutrons. Protons plus neutrons. Down here's where we write the atomic number, and hydrogen has an atomic number of 1. That's just the protons. So in a neutral hydrogen atom, I didn't put a charge up here yet. In a neutral hydrogen atom, the number of protons are 1, the number of neutrons are 0, and the number of electrons, because it's neutral, has to be equal to the protons. So in a neutral hydrogen atom, there is 1 proton in the nucleus, no neutron in there with it, and there's 1 electron whirling around it. Now, what happens if I put a plus charge here? Because Svante Arrhenius said acids produce H plus ions in solution. So what happens if I put a plus charge on there? Well, that plus charge, charges affect the number of electrons. So if I have a positive charge, I need to take away an electron. And you can see how H plus ion is actually just a naked proton. It's proton, and that's it. So literally, I mean, imagine a hydrogen atom that normally has a proton and it's got an electron whirling around out here, right? And it's an electron cloud, very small electron cloud. And then we're going to take away that electron. It is now literally just a subatomic particle. This is the proton floating around. Well, you can't have subatomic particles just floating around in a beaker of water, right? I mean, we're not going to have protons just floating around in here. And scientists have figured that out. What we now know happens is this. Hang on. Drop my eraser. We now know that the second a proton would form in water, we now know a second a proton would form in water, another water molecule from the solvent will come along, grab it, and bind to it, and actually form the H3O plus ion called hydronium. So as soon as an H plus ion would form in solution, maybe you're a visual person, as soon as an H plus ion forms in a beaker of water, a water molecule is going to come along and it's going to use one of its lone pairs to make a bond with it. Now, if we're writing that out in formula, it looks like this. And it's going to make this special ion. It's called the H3O plus ion, and it is the hydronium ion. H3O plus, hydronium. Yeah. So H plus not stable. It's so unstable, as soon as an acid would produce it, water uses one of its lone pairs to grab it, and it forms H3O plus. So instead, what Savante Arrhenius should have said is that an acid is a substance that produces H3O plus ions in water. And I got a slide here talking about that. So if I was going to show HCl, hydrochloric acid, being an acid, we should show the water, and the H gets added to the water to make hydronium and chloride. Now, I will say this, even though all self-respecting chemists know that this is what actually happens, right, where it reacts with the water to make hydronium, okay, we chemists are so lazy, we still write that. Because every chemist that's worth his weight, right, or her weight, knows that as soon as HCl dissociates, right, the H plus gets bound with the water to make hydronium. We are just so lazy. It is faster to write H plus than H3O plus. So it is perfectly acceptable to write either of these as the, way HCl dissociates in water. Technically, this one's 100% accurate, but chemists know H plus isn't real. And as soon as you see an H plus, it's just H3O plus. So you will still see me write it like this most of the time, because again, I know it's technically H3O plus. Cool. After Arrhenius came two, I believe Scandinavian scientists. I don't remember exactly where they were from, Denmark or something, Bronsted and Lowry. And they come up with an alternative definition of acids and bases. And this is a pretty darn good one. This is generally the definition that Chem 102 students like the most. And it's a powerful definition. They did a great job with this definition. I don't personally think it's as good as the Lewis definition, but people don't like drawing Lewis structures, so they don't like the Lewis definition. So, spoiler alert, we're going to be drawing Lewis structures here shortly when we get to that definition. But let's talk about the Bronsted-Lowry definition. Bronsted and Lowry got together, and they said that a Bronsted-Lowry acid is a proton donor, so it's the reactant in an acid-base reaction that gives away an H+. And they said that a Bronsted-Lowry base is a proton acceptor, so it's the reactant in an acid-base reaction that accepts the NH+. So if two species differ on a reactants and a product side of a reaction by an H+, we call them a conjugate pair. So Bronsted and Lowry were the first scientists to come up with this idea of conjugate pairs. And in fact, you know what? We're just going to do that right up here on the board. I'll show you exactly what I'm talking about. Look at this guy that we were just talking about. We'll do this one first. I'm going to use a single-headed arrow here. I'm going to explain why I'm using a single-headed arrow for this one. It's because HCl is a strong acid. We'll get there. If you use the double-headed arrow here, it's okay. Technically, this one only goes in the forward direction. Getting ahead of myself. Don't worry about the arrow right now. That's okay. Right. So go ahead and take a second, write that down. The Bronsted-Lowry definition of acids and bases depends on you finding first the conjugate pairs in a reaction. So what are the conjugate pairs? Okay, well, the first thing you have to do is figure out what reactant goes with what product. And this is usually very, 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 very easy, right? You just find the reactant and the product that look the most alike. So HCl, does that look more like H3O plus or Cl minus? Well, heck, it's got a chlorine in it. So HCl and Cl minus must be a conjugate pair. So they're going to go together. That's a pair. Okay, and I like to connect them with a bracket. You do you. And then H2O, which product does that look more like? Well, it obviously looks more like H3O plus, so that's going to be a pair. Cool. And now we're going to say what happened to these reactants. So if we look at HCl, HCl goes from HCl to Cl minus. It lost a hydrogen and a unit of positive charge. This guy's neutral. That guy has a negative charge. So it lost a unit of positive charge. So this guy gave away an H plus. Now, if we go back to the definition that Bronsted and Lowry give us for acids and bases, they said the acids are the proton donors. They're the ones that give away the H plus. So HCl must be my acid in this reaction because it gave away an H plus. Now we're going to talk about Cl minus here in a moment. Hang in there. Next up, let's look at this set. What happened to H2O? Well, it has gained a hydrogen. It's now H3. And it gained a unit of positive charge. Went from neutral to positive 1. So this gained an H plus. Bronsted and Lowry say the substances that gain a hydrogen accept an H plus, gain an H plus ion, they are my bases. So H2O is going to be my base because it gained an H plus ion. Gained an H plus. Okay, so now what is going on with the product side? Now I'm going to teach you the easy way, then I'm going to explain it. The stuff on the product side are called conjugates. And the conjugates are saying if the reaction were to run backwards, what would act like the acid or base? Now, here is the easy way, folks. If this is the acid, then its conjugate is the conjugate base. They are opposites. So if this is an acid on the reactant side, then its pair on the product side has to be the opposite, called the conjugate base. And if this is the base on the reactant side, then its a pair on the product side has to be my conjugate acid. And I'm going to explain why right now. Here's what this is saying. This is saying if the reaction were to go backwards, and this reaction doesn't actually even go backwards, but if it were to go backwards, then this would be acting like an acid and this would be acting like a base. Let's prove it. What we're going to do is we're going to write this reaction backwards. So we're going to make these the reactants, we're going to make those the products, and we're going to apply the same thinking that we applied to this to that, and we'll see if that is indeed true. So here we go. H3O plus Cl minus goes to HCl plus H2O. So what we would do is we find our pairs. H3O plus looks most like H2O, so that's a pair. And Cl minus looks most like HCl, so that's a pair. And then we have to say, okay, well, what happened to H3O plus? It lost a hydrogen, and it went from +1 to neutral. It gave away a hydrogen and a unit of positive charge. That's what acids do, proton donors, according to Bronsted-Lowry theory. And then what happened to Cl minus? Well, it gained a hydrogen and it lost a unit of minus charge. It accepted an H plus. That's what bases do. Now let's check it. We said that H3O plus was a conjugate acid. If it went backwards, it would act like an acid. Yup. And we said Cl minus was the conjugate base of this original reaction. We said if it was to go backwards, it would act like a base. We just proved it does act like a base. So the easy way to figure out what's the conjugate acid, what's the conjugate base, is identify correctly the acid and base on the reactant side, and then it's just the opposite, right? Its pair is the opposite on the product side. And then you can double check it if you want it. Let me give you another one. I want you to label the acid, the base, the conjugate acid, the conjugate base, and we'll check it. This one does get a double-headed arrow. I'm going to explain that later. Don't worry about the arrows. Okay, here's what I want you to do. I want you to pair them up. What does this go with? What does this go with? Now I want you to say, who's giving away an H plus? Who's gaining an H plus? Go ahead. All right, folks, here we go. HC2H3O2 obviously looks the most like C2H3O2 minus, so they go together. That's a pair. NH3 looks the most like NH4 plus. They go together. That's a pair. So now I gotta say, who is my proton donor? Who is my proton acceptor? Well, this guy gave away an H plus. That's my proton donor. That's the acid. And this guy accepts an H plus. That's my base. And now, if you did that correctly, getting the conjugates right should be easy. I mean, you got to put a lot of time into making sure you get the acid and base right. Because if you get them wrong, everything else is wrong, right? Because now we're going to say, well, if that's the acid, then this is its conjugate base. And yeah, I'm lazy. I'm going to abbreviate that CB. And if this is the base, then that's its conjugate acid. I'm also lazy. I'm going to abbreviate that CA. So a little conjugate acid, conjugate base work, right? So, a couple more to look at. If I put H2SO4 in water, right, it donates a hydrogen. So that's the acid. This guy accepts a hydrogen. That's my base. Same thing over here. NH3 in water. NH3 gains a hydrogen. That's my base. H2O loses a hydrogen. That's my acid. So very important to be able to identify acids and bases. So if we take a look at a conjugate pair, like an acid and a conjugate base, or a base and its conjugate acid, they differ by a single H plus, right? So what's the difference between H2SO4 and HSO4 minus? They differ by a hydrogen and a unit of positive charge. What's the difference between H2O and H3O plus? They differ by a hydrogen and a unit of positive charge, right? So they differ by one hydrogen and a unit of positive charge. That's the difference between conjugate pairs. So we actually just did the top one, right? Or essentially we talked about the top one. Let's take a look here at the bottom, okay? Which of the following of these is a conjugate acid, conjugate base pair? So in order to be a conjugate acid, conjugate base pair, you have to differ by a single hydrogen and a unit of positive charge. So take a look, 1, 2, and 3. Which of these, and it can be more than one, would indeed be a conjugate pair, something you would find on the left of an acid-base reaction and something you would find on the right. It's pair on the right of an acid-base reaction. So hopefully you looked at number 1 and you said, well, they differ by a hydrogen, and this guy's neutral and that guy's negative, and they differ by a unit of positive charge. Yup, that is a conjugate acid, conjugate base pair. Take a look at number 2. Hopefully you looked at that. You said, well, they differ by hydrogen, and they differ by a unit of positive charge. So, yup. And these guys aren't even close, right? I mean, they're not a pair, so that's a no. If they were a pair, right, it would have to be H2PO4 minus. That would be the conjugate of H3PO4. That would be the conjugate base. So hopefully you got that. Let me throw a couple up here, just a couple practice problems. Let me show you another way that we can ask about this conjugate stuff. So let's start like this. Let's say I give you some acids, and you have to tell me the conjugate base. So for example, we'll do a couple together. That's a B. Sorry, the Windex is still on there. All right. So let's say HBr is my acid. What is its conjugate base? Well, I need to take away a hydrogen and a unit of positive charge. So if HBr is my acid, then my conjugate base would be Br minus. Now, you only take away one hydrogen at a time. So for example, say my acid was H2CO3. So if the acid is H2CO3, we got to take away a hydrogen. So just HCO3. And it started out neutral. We got to give it a unit of negative charge. So I'm going to put a couple of these up here, a couple more, and you tell me what the conjugate base of these acids would be. Go ahead and try those out. Give me the conjugate base of acetic acid, bicarbonate, dihydrogen phosphate ion, and ammonium. All right, you are taking away a hydrogen and a unit of positive charge. So this guy's neutral. So that's just going to become C2H3O2 minus. Be careful, that guy's already -1. So we got to take away another unit of positive charge. I'll get out of my shadow's way here. So take away a hydrogen, that's CO3. And now that's a negative charge. This is now -2, right? Because it was already -1. Okay. Here we go. H2PO4. We got to take away a hydrogen. So that's HPO4. And once again, already -1. So now it's -2. And here, NH4 plus, the ammonium cations, polyatomic cation, take away a hydrogen, that's NH3, and now take away a unit of positive charge, it's neutral, it's just NH3, which is ammonia. So that's one way to ask these questions. Again, I consider like a half a Bronsted Lowry acid base, because it's only like looking for the pair. Right now, the other way, obviously, to ask it would be if I give you the base, then I can ask for its conjugate acid. For example, say I told you fluoride was going to act like a base. What would its conjugate acid be? Well, it would be HF. We need to add a hydrogen and a unit of positive charge. So let me give you a couple of these. Go ahead, give me the conjugate acid for those. All right, let's add a hydrogen and a unit of positive charge. So this is going to be HNO3, goes to being neutral. This is going to be bicarbonate, the polyatomic anion, add a hydrogen, and the -2 becomes -1. You don't have to write ones, obviously. Add a hydrogen, that's going to become H2PO4. And I actually messed up the charge. I am so sorry. What happens when I do these off the top of my head? That should have been a -2. So let's go back and fix it for what it should be. HPO4 should have a -2 charge. Now, if I add a 2 there, it's only at a -1. So that's my fault. If you had that as neutral, you got it right because I wrote the wrong charge. So sorry. We're going to add a hydrogen to that. That's going to become HSO4. And then the -2 goes to -1. And now let's talk about this. We're going to add a hydrogen to that. Now, maybe you wrote that hydrogen out in front. HNH3. It's neutral. Now it's going to have a positive charge. However, and you could totally write it like that, HNH3 with a plus charge, and I would take it. But usually we just write NH4 plus for that one, because ammonium that's how we write the ammonium polyatomic ion. So how do we do with those? Again, I messed that one up. So sorry about that. But how we feeling about, that should be easy, right?